Okay, so welcome to CSE 579, Knowledge Representation and Reasoning. My name is Ju-Hyung Lee. I'm an Associate Professor of Computer Science. Before we start, we'll look at the syllabus. So if you log into Blackboard, the syllabus was already uploaded there. So let's go there first. So today we'll talk about logistics and a brief introduction to the course. Okay, and feel free to ask questions if something is unclear. This is just the logistics that we have. So my office hours are Monday and Wednesday, 9 to 10. And our TA is Yi Wang. I don't see her here yet, but I'll introduce when she comes in. Her office hours are Thursday and Friday at Center Point. Okay? And I presume that you already have read a description about this course, and I'm going to talk a bit about this later, so I'm going to skip the description part. Okay? There is no dedicated textbook for this course. There is actually some textbook about KR, but it's a bit outdated. We used to have this as a reference, but I don't put it here. Instead, we are going to read some papers and some monographs. So here are actually the kind of books that this course is built on. Okay. So you may have seen some of these books before. We are not going to cover all the contents here, but we will try to organize in a way that we can learn in a coherent way. Okay. So one thing that I want to emphasize here is course materials are not to be distributed or to be sold for online sites. I know where the students actually send their solutions and worked out problems online. Anyhow, we are going to change a lot this semester, so that will not help you. But also, one thing that I want to emphasize here is when you think about the problem for yourself or by yourself, you learn something. But if you just read somebody else's materials, the written down solutions, that doesn't help much. Okay? So I'm emphasizing here that if you do this kind of thing, you will get the penalty. Okay? All right. So the topics that we are going to cover are these. So I'm going to talk actually more about this soon. But we are going to cover quite a lot of topics here. I'm not going to go through all of them in detail. So some of them deserve more attention. Some are kind of rough. That is basically how the field is matured in one area versus the other. There are some well-established area, and also there are some emerging areas. So I want to balance among those things. Okay, so this is the most critical part that you're here for today. Okay, so grading. So attendance is 10%. There will be two midterms, 15% for the first one, second one will be 20%. Homework is 25%. I'm going to talk about what will be the homework, and there will be a term project. Okay, so roughly this is the cutoff. Probably we'll just go with this one. 87 over is A, which includes both plus and minus. Okay, so if you want to be safe side on the A 0, then you should get like 90%. Okay. All right. Any question about this part? Okay. So what is attendance? So if you log into Socrative, that gives me who attended this course. And I want you to be engaged in this class. So, I mean, there are some things like if you have some distractions, then you may lose some point for attendance. So, I mean, you're a graduate student, so I don't have to emphasize these kind of things. Okay? But read this carefully. Okay? All right. So if you have some problems, I heard that some student who is coming from the East Coast, they have some flight delay, so they cannot make it today. I can understand. When you have this kind of incident, report to me immediately. Okay, don't wait after the class is over. Okay? All right. And there's a bonus credit for you. So here, there will be some class discussion problems. I will announce it beforehand. And if you have solutions for these problems, you can come to the board and write your solutions, and you can present. And we use Piazza, which I'm going to talk later. Writing the solution here is okay, but also I want those presenters to post the solutions online on Piazza, so other people can also go over this carefully. So these bonus credit consists of two parts: one successful presentation in class, as well as posting the solution on Piazza. Okay. And if you know already the solution, if you have seen the solutions somewhere before, then don't try to participate. There will be ample problems that you can do later. Okay. All right. Any question up to this part? Okay. All right. So there will be homework. There could be some problem solving, like some questions about the materials that we covered in class, or some mini programming that you have to do that uses some KR tools. Okay, so we are going to learn a couple of KR tools here, and you need to know how to use those tools to do some mini programming. Okay, and the homework is individual, so you are allowed to talk with your friends, peers, about the materials that is unclear. We can post on the Piazza together. All these kinds of things are okay. But when you work on the problems, when you write your solution, that should be by yourself. Okay? There's a critical difference between copying and collaboration. Okay? And this is actually required for all the instructors. If the instructor sees that there is a plagiarism or copying solutions, then we are required to report to the dean's office. Okay, so there will be no exception to this policy. Okay, so just be cautious. If you receive help from others, one safe way to avoid this kind of plagiarism is you write acknowledgement in the beginning of your homework. Okay, so I collaborate with these people, and he helped me understanding this part. So that is okay. That will not be penalized. Okay? Okay, and here, yeah, so the first time violation will be reported to the dean's office. Homework grade will be 0, and the letter grade will be get lowered by 1. Okay? So the TA, actually let me introduce the TA here. E1 is a PhD student in computer science. She is an expert in algebra presentation as well. Okay? So she will mostly do the grading your project and help you to do some project, the homework and project. So yeah, if we see that there are too many problems to grade, then we may choose some subset of problems. Okay, so that will be random. So you are expected to solve all solutions. Okay, but at the end we are going to give you sample solutions to all problems so that you can compare. Okay. All right, so there will be a term project, and here you may choose your own topic, or I can help you to find some topic. Okay. So here I can allow maybe up to 2 people in a team. So if you think that's a better way to go, that's fine with me. Okay. So it will be consisting of 3 parts. Initial proposal will be due around mid-semester. And there will be some progress report in maybe a couple of weeks later. And then final report is due at the end of the semester. Okay? So project is 30%. So if you are coming here for meeting the MCS portfolio requirement, yes, that can be counted. Okay? All right. So we have class Piazza page, and here, if you have any questions about the class material, some doubt, you can post questions there. TA and me will look at those questions, but you're welcome to respond to your peers' questions if you happen to know the answer. Okay, so that's a collaborative learning. And here, yeah, so anonymous posting is actually discouraged, okay, for many reasons. We are going to use Blackboard for the course materials and some important announcement. Okay, but other than the discussions will be posted on the Piazza because it's easier to access those discussion page on the Piazza than the one in the Blackboard. Okay. All right, and as I said before, we are going to use Socrative yeah, so you should be already logged into the Socrative. Okay. And if you have grading questions, don't wait until the end of the semester. We cannot remember what you did before. Okay, and so the policy is if there's a mistake in grading, come to us. Actually, I would encourage to meet the TA first because she knows better. So come to her within 1 week when the graded work was returned to you. Okay? All right. I do encourage you use laptop or tablet during the class if there's a valid reason. And also, actually, we are going to use Socrative, so that's the time that you have to use those tools. But other than that, I do see sometimes people do Facebooks and social medias. That's not necessarily have to be happening here. Okay, so you should know better. Okay, and this is just academic dishonesty that you should be familiar with. Okay, I'm not going to bore with you all this. Okay, any question up to this part? Yes.
Can you give one or two examples? What kind of projects were there in the last class?
Yes, we are going to do that maybe before, during the first half of the semester. Once you know some basic things about knowledge representation.
Okay, so give one example.
Oh, okay. So what could be an example? So some students who have a background in some particular area in computer science, they use some KR tools to enhance those areas. So one thing that I saw was some students who was in security major, he wanted to do policy analysis. So formal verification of policy. In case you don't know what is policy, this is actually declarative specification of the system behavior. And there is a lot of policy specification language, but there's not many work done on policy verification and also policy-based planning, things like that. So that's actually kind of combining both areas in security and knowledge representation. That was one thing. Another people did knowledge representation in robotics. So the robot has to do some high-level planning. So he was working on some robotics in low level, but also can combine the high-level knowledge on that. And there is also very I would say frequent topics usually try to model some formal specification of some system in knowledge representation tools. Some people do QA system based on knowledge representation, knowledge-based QA system. Okay, so some people do some workflow specification. So actually, let me tell you those things in more detail when we go through some topics. Okay. Yeah.
Are you looking for any specific prerequisite topics that you should be using the program before going into this course?
Particular topics? No, not much. I mean, we can talk about the interests that you have. Okay, right? There are some particular preference that I have in terms of research side. Okay, so for instance, like one of the last topic here is actually neural networks and knowledge representation, which not many people have actually tried yet. But that's actually very interesting research questions. Okay? Let me actually go over the course material, course structures, and then that will give you some more idea about it. Okay? Any other questions? Okay, so okay, so then let's go to course materials. Okay, good. Okay, so we just did syllabus, and if you came late, log into socrative.com, room number is CSE 579, and type your ASU right ID, and there's a keyword that you have to type in, which is start. This keyword will change every lecture. Okay? Okay, so lecture 1. So introduction to knowledge representation. So this is most non-technical part of this course, and could be fun. So AI 101, knowledge representation is an area of AI. And there are too many areas of AI, which contains also machine learning, natural language processing, research and heuristic, robotics, constraint satisfaction, planning, and so on and so forth. I don't actually have room to include everything here, but the AI is quite a diverse field. So what is the definition of intelligence? So this is dictionary definition, okay, which is not from the AI textbook. One dictionary definition that I found was saying that intelligence is the capacity for learning, reasoning, understanding, and similar forms of mental activity, aptitude in grasping truth, relationships, facts, meanings. Okay? So, sounds reasonable. Another definition is saying that the ability to apply knowledge to manipulate one's environment or to think abstractly as measured by objective criteria. So as you see here, there's a keyword that is relevant to this course, which is reasoning, understanding, grasping the truth, facts, meanings, knowledge, okay, to think abstractly. Okay, so these are actually very relevant part of knowledge representation. One thing that this definition tells us is we're not talking about animal intelligence here. Okay, so just recognizing some object. So cogito ergo sum as a French word for I think therefore I am. So this is what distinguishes humans from non-intelligent objects. Okay. So according to this definition, or following this definition, AI can be described as the study of intelligent behavior achieved through computational means. And knowledge representation and reasoning could then be viewed as the study of how to represent with knowledge in order to decide what to do. So here we are focused on knowledge rather than data. And knowledge representation and reasoning, often just denoted as KRR, or sometimes people just say KR, is at the heart of the great challenge of AI, to understand the nature of intelligence and cognition so that computers can be made to exhibit human-like abilities. Okay. So before we can start reasoning with knowledge, the first thing is actually to represent knowledge. But the interesting thing actually comes when you do the reasoning, because that makes the system to decide what to do. And so there's actually two sides in AI. One is the learning side, there's a reasoning side. So what is the learning? Very roughly speaking, learning is to learn the models or knowledge from the data. Okay? And what is the reasoning? Reasoning is manipulate such models and knowledge to derive certain new information that is not explicitly from the data. Now, ideal situation is the machine learns from the data, the knowledge, and then manipulate this knowledge to do something new. Current status is actually not quite there. There is actually some gaps between the learning and reasoning. So learning can give some knowledge, but this knowledge is not very usable for the knowledge representation. Okay. So let's think about AI system without knowledge. So currently, the vision is very matured area. So it can recognize some box region to represent certain objects. So like ImageNet challenge, you have the pixel diagram. And then the system can detect the class or the identification of these objects, so person, or dog, or chair. Okay, this is where the AI system is actually very good at now. Now let's think about asking questions to the system. So which could you sit in? Okay. So from the picture, it's not immediate which one is actually can be sit on or sit in. I don't know, maybe the person, we can sit on person maybe, or sit on the dog or sit on the chair, okay? Maybe that can be answered in some ways. What is most likely to bite what? Okay? Maybe person can bite dog. This is not impossible. But usually dog bite person, dog bite chair. But chair doesn't bite person. Chair doesn't bite dog. Okay? So this is actually not that easy. Okay? How do you know this from the picture? Okay? That's something that you have, but the vision system doesn't have. Which one is most likely to become a computer scientist someday? What is your answer? So if you ask these questions to vision system, it's actually outside the questions that they are considering at this moment, right? There's actually visual QA, which is a hot area these days, which intersects between knowledge representation and computer vision. And this is actually the kind of that area. But even in there, the questions are much simpler than this, okay? Critical one. Which one would you save if the house was on fire? Which? Chair or dog? Okay. So the question is, would you use a robot babysitter without knowing which of these three possibilities it would choose? Okay. So AI system without knowledge is really dangerous. And surprisingly, not many systems can actually handle this, or maybe not surprisingly. This was an article when TensorFlow came out. Here is the thing. So when you have, so the neural network is actually the key technology these days. But here's one quote. Suppose we train an artificial neural network to recognize cats. When it recognizes a previously unseen cat in an image, it cannot explain to us why or how it did this. And if the neural network fails to recognize a spotted cat, it's hard for us to fix the problem. We are not going to tell it something like change element, blah, blah, value from this value to that value, and that value to that value. I mean, currently that's what is going on in the neural network. You don't know how to correct its mistake, okay? So there was some article that neural network recognized that image as a cat, okay, and that was correct. And now somebody changed the dot there, and suddenly it is saying it's a dog. Okay, you cannot explain why. Okay. When AI systems make a bad decision, we need to be able to understand why they made decision and communicate with them to fix the problems. The problem here is without knowledge, this task is actually very difficult to do. Humans are very good at communicating through the knowledge. We don't actually communicate through the data. Okay, if you learn something new, that power is proportional to the distance, okay, from some experiment, that's a law that we found, and you just tell others that this is the general behavior. You don't necessarily tell them, repeat all the experiments that I did again. You don't say that, right? And also something like this, this is actually the cooking scenario. So A boils B, A slice B, A peel B, A saute B, A cook B, A chop B. Okay? So This is actually a bit of out of order, but this is actually what the system learned as a sequence. Okay, so I'm not a cook expert, but there's something weird about this sequence if you look into this carefully. We know that this cannot be happening. I mean, you should peel first before you boil. Okay, that's kind of common sense, but the machine doesn't have that kind of knowledge. Okay. All right, so we are going to talk about how these kind of questions can be addressed by using knowledge representation and reasoning. So far, I mean, KR area has been there for a while, okay? Actually, from the very beginning of AI, knowledge representation was studied. There are a lot of progress in the area, but also there is a lot of obstacles here, okay? So it's understandable because human knowledge is actually very complicated, okay? You cannot solve this within 60 or 70 years. Anyhow, this is the current advance. Researchers have explored general method of knowledge representation reasoning, and we found some fundamental issues across application domains. So there are some common issues that people didn't think was difficult and turned out to be notoriously difficult. So some of the questions like frame problem took like maybe 40 years to solve. Okay? We'll talk about those kind of problems later. Okay, and there are also specialized knowledge representation method that works on time, space, causation, and actions. And also there is some applications in knowledge representation, including question answering, planning, and the semantic web. So what is knowledge? So we understand knowledge by knowledge all kinds of facts about the world. Okay, the simplest knowledge is true or false, whether this is true or this is false. Okay, and we are going to focus on that in the first part of the course. So of course, knowledge is necessary for intelligent behavior. Okay, so what is knowledge? We are not going to go into this question for the time being, okay, because it's actually very difficult to answer. Instead, we are going to consider representation of knowledge. Okay. So here is an example. So there's a symbol that means something. So if you see the symbols like this is first aid, okay, John. This is a name, okay, but it actually means the person John. Okay, so there's a difference between the symbol and the actual object. Okay, so this is something that we have to distinguish when we do the knowledge representation. When you talk about John here, it's just a string. It doesn't entail everything about the John yet. Okay, you know about John's height or face, you know about that, but the symbol is not enough to represent this fact. Even John loves Mary, well, this is actually true or false, okay? But again, there's a lot of things, if you go into the very careful, which John that you talk about, what is the love? We are not going to talk about what is the meaning of love. In order to represent this kind of knowledge, we have to go into philosophy and those kind of things. We don't have time for doing that, okay? Or at least we don't know yet. So we are going to pretend that these kind of objects can be represented by some symbol, and then we will manipulate those symbols. Hopefully that the mapping is not too mysterious, and also the manipulation is not too far from the actual understanding. So yeah, the reason that we are doing this is if A represents B, then A is actually easy to access than B, because we actually abstract away all the nuances of B. So we'll focus on the symbol A. Okay, so we are going to look at the groups of symbols that stand for some proposition. And knowledge representation is the field of study concerned with the representation of the propositions that are believed by some agent. Okay, so that's the representation side. And what is reasoning? So reasoning manipulates symbols so that it can do something new. Okay, so the analogy here is use arithmetic. So 1011 binary representation for 11 plus 2 is 13. So given the symbols, you can do some operations. Same thing is for the reasoning. So the difference is instead of numbers, we use propositions or knowledge fact. So if we know that John is Mary's father, okay, then you can infer, even though this was not said in the original sentence, we can say John is an adult male. There's an implicit knowledge that can be acquired from this assertion. Okay? And we can actually do more on this. Once we have the basic knowledge, we can compose knowledge to derive new information. So, in that sense, reasoning is a form of calculation over symbols, which stand for propositions. Okay? So the proposition represent abstract concept, but their representations itself are concrete, so that we can easily manipulate. Okay, so here is the first Socrative quiz. Okay. All right, so here's a short sentence. If the train arrives late and there are no taxis at the station, then John is late for his meeting. John is not late for his meeting. The train did arrive late. True or false? There was a taxi at the station. Actually, this is too easy, so let's not go into waste time on that. It's true, right? How did you find out? How do you know?
Because John is not late for his meeting.
Right? So, informally, we actually understand what that means, right? Now, how do we make computers to do the same reasoning as what you just say? Okay, so there are actually multiple ways to solve this problem. One is train arrive late, and if there are no taxis at the station, try to prove a contradiction. Suppose there was no taxi at the station, then according to the first sentence, the train arrived late is true, and there was no taxi at the station is also true. So that you can say that John is late for his meeting. But there is another fact that John is not late for the meeting, so that's a contradiction. So one way to go is a proof by contradiction. If you negate this conclusion, there was a taxi at the station. Negate it, then you get there was no taxi at the station, and put it into the knowledge base, suddenly knowledge base is inconsistent. So what is wrong? Assuming the knowledge base is correct, what is wrong is your ad hoc addition of this conclusion. So that conclusion has to be negated. Okay? That's what you do. Actually, you don't need AI system to do that, but if the symbols become more complicated and the story becomes more than this, then humans suffer. Okay? So one way that this can be solved in AI is to use formal logic. Here we use propositional logic, which many of you may be familiar with. So these hypotheses can be represented as three formulas. So train late is a symbol which denotes the fact that train arrived late. Okay? This is either true or false. Okay? Taxi is a symbol to say that there was a taxi at the station. Note here that I simplified a lot here. So when I say taxi, I meant there was a taxi at the station. I didn't mean that there will be taxi at the station, and there are 5 taxis at the station. I don't mean that. I'm just saying that there was a taxi at the station. Okay? So these kind of fine-grained details will be actually abstracted away. Okay? So that by saying one symbol, it represents a certain fact. And you see that this symbol negation, meaning that so if there was a taxi at the station, then negation means there was no taxi at the station. Right? So if that is the case, this symbol is called implication. If this is true, then this is true. Okay? So if train is late and there was no taxi at the station, John is late for the meeting. So this is kind of knowledge representation. Okay? You already know how to do. Okay? The next one is, again, is simple. So John is not late for the meeting. So it's a negation of John late. Train late. Okay, so train arrived late. So you can write simple fact like this. So the previous English statement can be written in 3 lines of the formulas. And once we turn this into logic, there's actually well built-in meaning for this conjunction, implication, and negation. Okay, so you can use those operations to derive new knowledge. Now, the conclusion that we wanted to derive from the knowledge base was there was taxi attestation. Okay, so you will learn soon how the computers can solve this problem. Actually, I already introduced one method. Now, let's actually look at something else. So if it is raining and Jane does not have her umbrella with her, then she will get wet. Jane is not wet, it is raining. True or false? Jane has her umbrella with her. That's true. How do you know? So when you think about this, you imagine Jane. You imagine umbrella, right? And you imagine that somebody get wet. Okay? Which was different from the train example. When you think about train, you think about train and John and meeting. In fact, these 2 examples have identical structure. Okay? If you use the propositions to represent each of these facts, like here I use P to denote the train is late in the first example, while in example 2 it is raining. Okay? Q represents a taxi at the station, and in example 2, Q means Jane has her umbrella with her. And R means that John is late for this meeting in the first example. Jane gets wet in the second example. But once you have the symbols, then you write the same knowledge. Okay? So the knowledge base is exactly the same. That's strange. I think I had enough power for the things. Anyone has a charger for Mac? Thank you. Okay, hopefully I can do that on time. All right, so as you see from this example, it does not matter what PQR stand for here. All right, so here we have the representation side and the word. Thank you so much. You get more. Okay, the problem is, okay, that's nice. Okay, hopefully this is charging. Okay, thank you. All right, so on one side, we see the actual world. And from the aspects of the real world, some other aspect of real world follows. And what we are doing in knowledge representation is we represent these aspects as a sentence in some formal language. And this sentence can entail another sentence. Okay? So why knowledge representation and reasoning is useful? Okay. So we can understand the behavior of system by the knowledge that it has. So if the system behaves in certain ways, it's because it knows in some ways. So you can query the knowledge so that why the system has made that decision. Okay. And we can also generate the behavior of a system. So for instance, in planning, you tell the system that what are the effects and preconditions of actions. And then you tell the system how this robot can go from here to another. Okay? So the robot can make a plan based on the knowledge that it has. And the declarative knowledge can be separated from the possible usage. and that is in contrast with procedural knowledge. So in procedural knowledge, you say, if this condition is true, then do this. Okay, so you write a bunch of if-then statement. But in the case of knowledge-based system, you can actually find a new way to solve the problem. Okay, so in the procedural way, you have to predict all possible combinations, and if the system is in the situation that is not in one of those possibilities, it fails. But in knowledge-based system, it can infer something based on what it knows, and it can still do some reasonable behavior. Okay? So it is actually less brittle than procedural system. And when the system has knowledge, it's actually also easy to debug. Because if it fails, then you go to the knowledge base and update this knowledge. Okay? And modification and extensions are also much easier to do. So here's an example to illustrate this point. So there are two programs. They are prologue programs. The first one and the second one. Okay? So you don't have to know the prologue. We are not going to go into the prologue in this course. Although Prolog was actually one of the influential language in knowledge representation. So let's see. Even if I don't tell you much about the Prolog, which program do you think has more knowledge? Okay, so in order to help you to understand, let me read this code for you. In Prolog, it works as in an interpreter-based way. So you ask the system some query, and then system tries to prove it. So you can actually say print C snow, which means I want to know the color of the snow. Okay? If it's feed into the first program, the Prolog will see the head that matches, and then execute the body. So it goes from the head to body. So this one matches the query here, and this is so-called Prolog cut operator. We don't have to know this, but basically it is committing to this clause only. So when the head matches here, it says it's white. Okay? So the system can answer the question, what is the color of snow? Okay? So same way, what is color of grass? What is color of sky? What is color of John? What is color of desk? Okay, what happens to the color of desk? It actually goes to the last thing because it didn't match any of this. This X is a variable that matches everything that is remaining. So it says beats me. Okay, so this is actually one thing. Does the system actually know the color of the snow? Well, if you want to actually enhance this system, what can you do? Now let's contrast this with the second program. In the second program, it's a bit more complicated. So print C of X. So if X is, let's say, is a snow, okay? So same query, then it matches here because X is a variable that can match anything. And it will find in the database what is the color of X, which will be denoted by this Y. And it will print whatever that Y. Okay? And in Prolog, there's also the database fact that you can state. And here, when you say color of snow, then it will try to match here. So it will find Y is white. So it will print out is white. Okay? If I ask color of sky, same thing. It will look for the color of sky matching with yellow. So Y will be instantiated with yellow. It will print out is yellow. So in terms of these two queries, these two programs operate in the same, outputs the same thing. Okay? However, it can be, this one is a bit more intelligent. So X, the color of X is Y if X is made of Z and Z has a color Y. Okay? So you can infer the color based on the component that it has. Okay? So you can say grass is made of vegetation and vegetation color is green, so you can infer these things. Now, obviously, the second program is more versatile, and if you want to incorporate more objects into this scenario, it's easy to do. In the first program, if you want to add new object, then basically you have to write another print C clause. Okay? Now suppose you have, say, an object that consists of 5 elements. Okay? Then in the first program, you have to give all the 5 elements and their colors so that this one is also blue and red and so on. Okay? You have to write 5 lines to say that this object has 5 colors. In the second one, you don't have to do, because this sentence is actually retrieving all colors that are associated. So it's actually more easier to maintain. Of course, writing this is easier for the novice programmer. This way is more difficult, and that's what we are going to learn in this semester. All right. And this is actually what I said already. So why not use the first program? In the second program, we can add new tasks and make them depend on the previous knowledge. We can extend existing behavior by adding new facts. We can easily explain and justify the behavior. Okay. So there was actually reasoning, a small reasoning in that program. There was no explicit statement about the color of grass. Okay, if you go back to the program, oops. There's no color of grass to be green, unlike the first program. But you can infer that grass has a color green based on the knowledge that it has. Okay, so in general, many facts will be there only implicitly. And the fact is, you cannot store all the relevant information in the knowledge base. There are so many things that you have to store. Think about this way. So if the robot goes to the new place and it has to do new operation, you don't know the environment. So you cannot predict what will be there. Okay? So if you write this in terms of the non-knowledge based approach, basically you have to enumerate all possible scenarios. And that's actually very huge. You cannot even fit into the memory. Okay? So in that sense, you can store the behavior of knowledge in the memory, and then the robot can use that knowledge to do certain decision. Okay. And here we use concept of entailment and logical implications that you already see in the example. Okay, so yeah, this is what I just said. Can we compute all implicit fact? It's not feasible to do. Okay, so the role of formal logic. So we are going to use logic in the first part. In fact, the logic was actually the main vehicle for knowledge representation for a long time. There's a lot of work that is built upon logic. Okay. How many of you know what is propositional logic? First order logic? Only 2? Come on. Okay. So if I say, is it new to you? This is called first order logic or predicate logic. Have you seen these formulas? Okay. No? Okay. All right, so if you are in that category, if you haven't seen this kind of formalism, I think you should speed up. Okay, so we will go over the review of this material, but that will be very quick. Okay, so. All right, so I'm going to post some material so that you can read and browse your memory. Okay, if you don't know what is first order logic, come to our office hours. Okay, that's very necessary to do. We will actually go over some basic topics here. Okay, so all propositions are represented as formulas which have a semantics according to the logic in question. Formal logics give us a framework to discuss different kinds of reasoning. So there is a lot of different kinds of reasoning. Okay, so deductive reasoning, model finding, abductive reasoning, default reasoning, epistemic reasoning. So let's actually go over a bit of it. So just to give get a flavor what this reasoning, different kind of reasoning means. The one that you saw in the previous training example is actually the deductive reasoning. So you derive some conclusion from the knowledge base. Okay, so deriving implicit entailed facts from a given collection of explicitly represented facts. So this is actually logically sound. Okay, there is actually the proof theory that has been developed by mathematical logicians that say what information that you can derive from those propositions. Okay, so there is a sound and completeness that has been studied in the area of mathematical logic, and that carry over to knowledge representation. So you can talk about the logically sound deduction and also complete deduction. So what that means is the reasoning can find all true fact. That's called completeness. Soundness means all the information that is derived by the reasoning is actually true. Okay? So this is actually common topics in logic. I'm not going to go into the detail, but basically, as I said here, the sound reasoning means the whatever the system derived should be meaningful. And the completeness is actually opposite. All the meaningful facts should be derived by the system. Okay? Now, this is actually ideal situation, but it's actually not the case for some part. Sometimes we want logically unsound derivation. So there's some uncertainty in the world, so you can never make the sound derivation. So sometimes we want to sacrifice some part of the soundness. And also, completeness is something that we also want to forget for efficiency reason. Okay? So even for the very simple reasoning task, if we want to do exact manner, that's actually exponential in the worst case. So you cannot actually wait forever to find the answer. So you have to give up those completeness assumption. And we'll see that kind of thing happening in when we go into the course materials. There's another thing called model finding and satisfiability. So here, this is a typical thing in the planning and configuration test. So we are given a set of constraints and a goal specification, and then we have to find a solution that satisfies all the constraints. So this is not the derivation. It's just that what are the solutions that make sense to satisfy all these conditions. So here's an example. Let's see who can solve this fast. Okay, so I'm giving you some clues, and you have to find the consistent model for this problem. One is the object here is either round or square. It's either red or blue. If it is red and round, or if it is blue and square, then it is wood. If it is blue, then it's metallic. If it is square, then it's not metallic. Okay? If red, then it's square. Now, what is this object? Well, this is kind of puzzle that you already play when you were young, right? So there's a bunch of clues you have to find which one is actually the thing that makes sense. Okay, let me give you some time to think. Okay, anyone has answer? Or just one person? Yes. Red and metallic and square. So let's see. Red, metallic, square. Is it good? So let's check it. Oh, you're too fast. So let's go slowly. Okay? So either round or square. So that's fine because that satisfies the first one. Red or blue? Okay, red or blue, correct. Okay, if red and round, then it's good. But it's red and square, so it does not actually apply here. This one doesn't matter because if condition is false. If blue, then metallic. Blue, but it's not blue, so this one doesn't mean anything, right? If square, then non-metallic. Square, then not metallic. Okay, so that didn't work well. Anyone else? Yes. Round, blue, metallic. Okay, so let's go. Round is fine. Blue is fine. Red and round. So, well, blue and square. So the third condition does not apply either. Blue, then metallic. That is fine. So we say blue and metallic. That's fine. If square, then not metallic. But it's round. So this one does not fire. If red, then square. If red, then square. So, no, actually. If red, oh, yeah, so that doesn't apply, right? Okay, so that is one. Any other thing? So, in fact, there's also another answer that have here. That is actually the same as the solution that I have, but I don't know. Maybe there could be another solution too. In general, there could be multiple solutions that satisfies all the constraints, right? And this is different from the deductive reasoning. When deductive reasoning, whether this follows from the previous sentences, this is only one conclusion, either true or false. But here, you may have multiple models that satisfy the constraint. So this is not a sound reasoning. You cannot say that from this description, this object must be red, metallic, blue. Oh, actually, okay, sorry. I found actually different solutions than what you mentioned. Okay, anyway, so there are two solutions that we found so far. So each solution is not actually entailed by the description because it could be another thing, right? But each one makes sense if you plug in to this constraint. Okay? So these are possible assignments that satisfy all these questions. That is called model finding and satisfiability. And in case you didn't, you're wondering, this can be done also in propositional logic, and satisfiability in propositional logic is NP complete. So you just solve one NP complete kind of problem. Okay? So the question why this was more difficult than the train example is because there are more symbols. And as you know that as an NP complete problem, if the size of the problem becomes large, then in the worst case, you have to use exponential time to solve this problem. Okay? Yeah.
So in the example that you've given, you gave options between metallic and wood, right? But in the solution that you've presented, another variable is not metallic. So in that case, would that...
Well, metallic and not metallic and wood are not necessarily negation to each other, but you can do that. Wait, don't go too serious about this example. Just to give some idea about the different kind of reasoning that we are talking about. Yeah. Okay, now what is abductive reasoning? So there's an inference to the best explanation. That's a short sentence to say. Think about diagnostic task. So you know the possible system behavior, and you want to find out the good explanation about what happened. Okay, so let's see what are the... Okay. So given a background theory and a set of possible explanations and what you observe, you want to find most likely set of explanations. So here's an example. Earthquake implies alarm. Burglar implies alarm. Now, this is some technical terms, abducible. So we don't know whether this is true or false. Earthquake was there or burglar was there, but in case it's necessary, we'll assume this to be true in order to make the explanation to be possible. Okay? And alarm is observed. Okay? So this is the, let's say, so this is the background theory that you already know what is in the domain. And this is the set of abducible, which we don't know whether it is true or false. Okay, but you can tentatively assume to be true in order to make an explanation. Now you observe that alarm here. Then what is a possible reason for this alarm? One possible reason is, of course, earthquake. Another possible reason could be a burglar. Okay, this is what you already do. Okay, if some system failed, if you have a system failure, then you want to see what is the reason for this failure. You don't know whether it's true or false, but you can assume that and then try to see whether that makes a consistent story. Okay. Again, there could be many possible explanations, but each of them is also not sound inference. It could be a different result than what you think. Okay, there's another one called default reasoning, and this is called jumping to conclusions. Okay, often we do not have enough information, but nevertheless wants to reach a conclusion, and what is likely to be true. And if we don't have evidence to the contrary, we just assume that something to be true and we jump to a conclusion. That's what actually humans are very good at. So typical example, toy example is this Tweety example. Birds are usually able to fly, okay? And Tweety is a bird. Then you jump to conclusion that Tweety can fly, right? However, Tweety can be a penguin. Does that make sense? Let's say name Tweety is a penguin. So then you derive that Tweety cannot fly. Okay? Okay. So this kind of reasoning is not actually checked in detail. So we said birds are usually able to fly, but we don't know whether Tweety is a typical bird. Okay? But still, you assume, based on the information, you assume that Tweety is able to fly. Okay? Similar example in the history of AI was Getting to the Airport example by John McCarthy. How many of you heard this story? Okay. So this is one of the oldest planning problem in AI, where the problem is just this. So you are sitting on the desk at home and you wanted to get to the airport. How can you get to the airport? And there was actually another sentence was, there was a car in your garage. What do you expect? How many of you are human here? So the typical answer is walk to the car and drive the car to the airport. So people try to inject this knowledge into computer so that computers can find the same answer as humans do, and found out there's a lot of problems here. What is a problem? The computer said, I cannot actually verify what you're saying is true. Because what if when I walk to the car disappears? Okay? Because you didn't say the car will remain there. You have a common sense knowledge, if you don't say anything about the car will stay in the same position. That's what you do as a jumping to the conclusion, but computers don't usually jump. Okay? Now, let's say that, okay, then, you know what, the car will be there, don't worry. Then the computer will also say, I still cannot verify your statement, because what if the car is broken? Okay? So then you cannot get to the airport. Or then you can say, oh, yeah, don't worry, the car is not broken. And then the computer still says, I cannot verify your statement. Why? Because what if there's no gas in the car? Okay, and I said, no, it's okay, it's run by electricity, don't worry about the gas. Still, the computer say, no, what if the airport disappears? Because you didn't say the airport will remain there. Okay? So no matter what you do, the computer will always find a counterexample to your claim. And enumerating all these facts to avoid counterexample is very difficult. Right? On the other hand, when you talk about, this is actually very natural. When you think about mathematics, where this mathematical logic was derived, in mathematics, you don't usually say, actually, I don't see any theorem in mathematics saying that usually if P is true, then epsilon exists. You don't usually say that, right? Okay? So usually or normally is not something that you find in the math textbook. However, humans make such a decision a lot because we cannot enumerate all possibilities. Okay. All right. So what default reasoning is about is you have to still jump to the conclusion based on the limited knowledge. Okay. How do you make computers to jump like what humans do? That's what default reasoning is about. Again, this is unsound conclusion. There could be a wrong answer. So if you want to stick to the soundness every time, then you will be in trouble. So this is another example that you want to retract soundness in your reasoning. Okay, this is also called non-monotonic reasoning, the technical term which I'm going to explain later. Okay, let's see. We have about 10 minutes, and I think I can do. This is epistemic reasoning, and it's a reasoning about knowledge. The typical example here is called multi-children puzzle. Have you seen this puzzle before? How many of you seen? One, okay. Two, okay, good. So in case you haven't seen this, this is one statement. So 10 children are playing together outside. After playing, they come inside, and their father says to them, at least one of you has mud on your forehead. Now, each child can see mud on others, but he cannot see himself or herself, right? Okay. And the father then asked this question, do you know if you had mud on your forehead? The children answered no. Then he asked the same question again. Then now some children says they know whether they have mud on their forehead. How many children answered yes? How many? No?
Everyone would have said at most
Hmm?
at most 9 children.
At most 9 children answered yes? No, that's not correct.
I heard a similar one to this.
Uh-huh.
It would have been the number of children minus the ones with the mud.
No.
No?
No. There is actually only finance cases 1 to 10. So whatever that you say, ultimately you will get to the answer. So let me just tell you the answer. It's actually 2. Why? Well, imagine that there was only 1 children. What will happen? So let's see. So suppose you have 1 children that has mud on the forehead, and let's say there are 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So suppose this was the situation. Then what will happen when the father first asks the question? Now, if you have those children here actually sees one of the one of the children have mud on the forehead, right? But he doesn't know whether, or he or she doesn't know whether he or she has mud on the forehead, right? So these people cannot say yes. However, only this person can say yes, because the father said, at least one of you has mud on the forehead. But from this child's point of view, none of the other children has mud in the forehead. So it must be him or her, right? So the child should raise the hand in the first round. But it didn't happen that way, which means that this is not the situation. Now, what if there was 2 people and okay, so then in the first round, okay, again these guys cannot answer, okay, because they do see 2 of them has mud, but he could have mud on the forehead too. Now, if you look at this person's point of view, he also cannot answer yes now, because he also sees there's another person, one person actually, at least one person has mud on the forehead. But it could be also him that has forehead. But now if you look at from this person's point of view, the other guy didn't say yes, which means that this guy, same reasoning, he actually sees that you have mud on the forehead. Okay? So at the first round, they cannot say yes. However, in the second round, now they know that, oh, then he can infer that this guy actually saw my mud in my forehead. So then in the second time, both of them can say yes. Okay? And in general, you can prove this claim that if there are k children on the mud on the forehead, then at the case round, they can, those children that has mud on the forehead can say yes. Now, I'm not going to go through this in detail now, and also we are not going to touch on this topic in this course, but this is actually one of the areas in knowledge representation. It's very sophisticated because it's not only about the fact, but you have to talk about the knowledge that the other agent has. It could be very interesting from the adversarial reasoning. So if your opponent wants to attack, then what is the knowledge that it has, and so on and so forth. Okay. All right. Okay. So in the remaining few minutes, I'm going to talk here. Maybe I will not explain everything today, so I will continue next time. But here is a course structure. So we will have three foundations, where the emphasis here is more on the blue part than the green part. We will first talk about the classical logic, okay, because this is not readily usable as knowledge representation, but it actually influences a lot in the knowledge representation. So most of many of the KL formalism are based on this one. The first topic after this we're going to see is answer set programming. And then we will go to the ontology, okay? And then we will go into the probabilistic theory where the knowledge representation on the uncertainty is actually considered. Here we are going to we are going to study a formalism called Markov logic that combines both logic and the probability. Okay, and also we'll study LPMLN language, which combines these two things. And the green part is actually a bit quite new, so we are not going to spend too much time on it, but and I'm not going to, we don't have time to go over the basics of neural network, but assuming some basics, I will talk about some recent trends that goes between neural network and knowledge representation. Okay, so let me just browse this for now, and I'm going to go through detail later. So we are going to talk about classical logic, okay? So, and then we'll jump into the knowledge-based declarative programming, where the idea is you want to model the problem as some representation form, and you can apply the so-called answer set solvers to find the solutions, okay? So this is what we are going to do. And the next topic is actually ontology. There's a lot of very large ontologies these days. Some of them has been used in the QA system, like Watson, that won the Jeopardy show. So we are going to study the formalism in that area, which is derived from the semantic web area. And we'll talk about RDF and Sparkle, okay, and OWL, which is a web ontology language, and description logic, which is basis of OWL. After this, we go into the uncertainty part that you saw in the picture. So probabilistic graphical models, there are actually two things, Bayes net and Markov net. One is directed model and the other is undirected model. And I'm going to skip this. So we are going to complete this part. Okay? All right. So sorry that I had to rush in the last part, but basically I will go over each of these things more detail next time. But starting from next class, we are going to go into the technical materials. And for that, we will cover propositional logic. If you go to the Blackboard, I put course schedule there, and I put also the reading materials for this class. So first thing that you have to read is classical logic, handbook of knowledge representation, chapter 1. I think I put the link to that paper in the Blackboard, so look at that paper. The slides will be posted before the class. That will be kind of alpha version. After the class, I will post the final version on the Blackboard. Okay, any question? All right. So then I will issue the exit ticket. So if you log into... Okay. So there will be 3 questions. And the first one is how much did you understand this course? And the second one is, I forgot, what did you learn in today's class? You can just write a brief sentence or keyword there. The third one is, the third one is, please answer the teacher's question. I cannot actually change this format, but what I actually want to intend for the third one is, do you have any questions about today's material? So whatever the questions that you have, you can put there. So I'll take a look at it, and I will respond on the piazza. Okay? All right.
Can you repeat the third question?
Yeah, so the third question, okay. Third question is here. Okay, so do you have any question about today's materials? So ignore the comment there. I mean, this is actually the paid application. I already paid like $60 for this app. Okay, but I cannot actually modify this question. Okay, so just say, just pretend that do you have any question about today's materials as the last one. Okay. So I close this exit ticket maybe half an hour later, so you can feel free to update if you need it. All right, then if there's no question, thank you and see you next time.